Okay, so we talked about the Boyle's law, and we said that it's a relationship between the gas pressure and volume. That's an inverse relationship. Generally speaking, any law or principle is important in this chapter. So how do we breathe, or how do we ventilate? And what's the difference between breathing and respiration? What's the difference? Is it the same thing? It is not. What does it mean? What's the difference? Breathing means? Yes. Breathing is a mechanical part. Inspiration, expiration. You inhale and exhale. That's it. This is called breathing. Okay? Respiration is the movement of oxygen and carbon dioxide in and out. So it can be external respiration, crossing the alveolar membrane. That's called external respiration. Or if you're doing so at the level of the cells, so oxygen going to the cells, carbon dioxide moving out, like out of the capillaries to the cells, and carbon dioxide moving from the cells to the capillaries. This is called the internal respiration. Okay? So how do we breathe mechanically? Okay? You can still call the breathing, sometimes you call it respiration, but it's more, if we're talking about external and internal respiration, it means the exchange of oxygen and carbon dioxide across the membrane. Which membrane? It depends. If you're talking about the external, that will be the alveolar membrane. If we're talking about the internal, that will be the capillary and cell wall. So we have inhalation and exhalation, which is inspiration and expiration. These are the two movements. And the reason why we talked about Boyle's law is to explain this. If you understand what's Boyle's law, this will make sense. So when you breathe in and out, here what you're actually doing. You breathe in, inspiration, okay? You do like this, right? You're expanding your chest. So what happened to the air inside? What's the pressure of the air? Does it go up or down? Down, right? So it will be less than the atmospheric pressure. So the air moves in, right? When you exhale, you're reducing the size of your chest. So what happened to the pressure of the air? Increase or decrease? So it will be above the atmospheric pressure, and it's going to leave. And this is exactly what we're doing, and this is why we talked about the Boyle's law, because this is exactly explaining how we do inspiration and expiration, or inhalation and exhalation. Okay? So you expand, and when you expand your chest wall, what is adherent to the chest wall from inside? What's lining the chest wall from inside? Parietal pleura. And what is adherent to the parietal pleura? Because of the fluid in between, the two glasses mechanism that we talked about. So the parietal pleura, what's adherent to it? Visceral pleura. And the visceral pleura is adherent to the lung. So when the chest moves out, expand, the parietal pleura will expand, the visceral pleura will expand, it will pull out the lung, increasing the volume of the chest, pressure goes down, air moves in, and the other way around. Okay? This is how we inhale and exhale. And this movement, when we say inhale and exhale, you're expanding using the respiratory muscles or the chest muscles plus the diaphragm. When you inhale, does the diaphragm move down or up? Down. It's like this. This is your diaphragm, it's like this. And when you inhale, you do like this. So you're increasing the size, increasing the volume, right? On the other hand, the chest wall will expand, so the whole size of the chest will increase, okay? And that will drop the air pressure inside, air moves in. And when you exhale, the diaphragm moves up, making the size of the chest smaller, and the chest wall itself return back to normal, and it is basically passive. You do some effort to inhale, right? You're using your muscles to inhale, but exhalation is kind of passive, just let it go, right? Unless, and we will talk about the details. if you're doing extra effort. You have to do some effort to exhale. But normally if you inhale, just let it go. Passive, right? You don't use muscle. But if you're inhaling, it's an active process. So inhalation is active, exhalation is passive. So compliance of the lung is basically the expandability. Is it expandable or not? Like, which is easier to be expanded, the balloon or the tire? Car type. The balloon, right? So it's more expandable, it's more compliant. So if it is more compliant, you don't need a lot of force. Can you fold the balloon with your mouth? Right? You can. Why? Because it's easy. Because the balloon, the wall is too thin, so it's easy, it's compliant. Can you do that with the car tire? I don't think so. You can't. Even if you put some air, it will come to a point that will be too hard. Why? The compliance is less. Why? Less expandable. Why? Because it is thicker, right? So this is the compliance of the lung. Connective tissue will play a role, surfactant will play a role in this, and the mobility of the thoracic cage will play a role. These are the factors together that affect the compliance, the expandability. Can you easily expand your lung or not? Depending on what? Connective tissue. Level of surfactant. If you have less surfactant, what happened to the compliance? More or less compliance? Less surfactant. Less compliance. Because the surfactant increases the compliance. If you have more surfactant, okay, you are increasing the surface tension and you can easily inhale and exhale, or you can easily expand. So that affects the expandability. If you have limitation of your thoracic wall, example, older people, there are joints here, right? We know that from 233. There are joints in the chest wall, joints between the ribs and the sternum, and in the back between the ribs and the vertebra, right? Vertebral column. These joints will become stiff in elderly, so it makes the movement harder. So the expandability will be harder because they can't even inhale. They cannot move the chest wall as they were when they were younger. So connective tissue, surfactant, and mobility. Generally speaking, we have different ways to report the gas pressure. Just the name is good enough. And this pressure. Just know that there are other ways, but this is what we have to know. Millimeter mercury, the atmospheric pressure, this atmospheric pressure, 760 millimeter mercury. Know that it can be torr, it can be centimeter of water, it can be pound per square inch. Yeah, these are alternatives. The name. But what we have to know, 760 millimeter mercury. So this 760, if this is the case, if this is normal, it's 760, you call it 1 atmospheric or 1 atm, ATM, okay, or P atm, which is the sea level. 760 is measured at the sea level. So guess what? If you go up to the mountains, if you go to a higher places, and actually within each state, there are some places that at the sea of the level and some other places that in higher, right? So you can't say it's all 760. You have to put specific measurements. It's 760 or 1 atm or P atm only if it is the sea level. Okay? If you move up, the pressure will increase, and that's not good for breathing. Okay? Because you need to make more effort to inhale and exhale. So the atmospheric pressure change when you change up or down, above or under the level of the sea. If it is exactly at the level of the sea, that will make it 760 or 1 ATM. The intrapleural pressure. The intrapleural pressure is the pressure not in the lung, but intra-alveolar pressure or intrapleural pressure. This is the pressure inside, and this is usually -1 in inhalation and goes up in exhalation, +1. So you go -1, +1, -1, +1. This is how the variation occurs. So normally it's -1, +1. Can you increase that or decrease it? Yes. If you are sitting down right now and you're breathing in, out, lightly, you're relaxing, you're not making effort, +1, -1, +1, -1, okay? If you are walking, jogging for example, it goes more, maybe +3, -3. If you're running, +10, -10. What is your maximum? This is the maximum. Okay, and this will include using everything in your power. Okay, like straining. If you wanted to exhale more, okay, you go like this. This is inhalation, exhalation. Can I do more? Yes, you can do like this. Right? To the extent of straining. This is the maximum that you can get, and this is actually dangerous. We're not supposed to do that because at this level, the pulmonary tissues or the lung tissues can be actually destroyed if that's the case. So intrapulmonary is different than the intrapleural pressure. Intrapulmonary, which is the intra-alveolar, this is the pressure within the alveoli, and this goes +1, -1. Intrapleural pressure is something else. If this is a lung, what is this? Surrounding the lung? Which membrane? Visceral. And what is this? Parietal. The pressure in between those two, the air pressure, is called intrapleural. In between the pleura. In between the parietal and visceral pleura. And this is always negative. It cannot be positive. It has to be negative all the time. Why? Because you have to keep the parietal pleura from one side and the visceral pleura from the other side. You have to keep the pressure in between negative so that they don't leave each other. Do you remember when I talked about the two pieces of glass that's flat and you put some water in between? These stick together, right? Because of the negative pressure that's in between those two. If you put something like a pen or a screw or something in between those two, they will separate. What will happen? You're introducing some air. You're increasing the pressure. So the pressure has to be always negative in order to keep those two layers stuck with each other. You have to keep the pressure in between negative. Negative doesn't change, yes. The average is -4, but it can go like from -2, -6, okay, -3, -5. Yes, you have variation, but all of it is negative. It has to be negative, okay? So if the average is -4, so let's say you're sitting down right now, okay? And after exhalation, this is my pressure. When you measure in between, let's say this is -2, okay? -6, -2, okay? So this is what we're doing now. Can you do more than that? Yes, instead of doing, I can do like this. You're making it more negative. The maximum that you can do when you inhale is -18. Okay? But it has to be negative anyway. If at any time, if the intrapleural pressure becomes positive, the two layers will separate. So what? What was keeping the lung inhaled? Why the lung is like this? Why does the lung does not collapse? Even though we know that the structure of the lung is like a rubber band. If you let it go, it will collapse, right? As long as you're holding rubber band like this, it will stay. Let it go, right? Same thing for the lung. As long as you're expanding the lung, you're forcing the lung to expand because the lung is attached to the visceral pleura, and the visceral pleura, there is a negative pressure between the visceral and the parietal pleura, and the parietal pleura is adherent to the thoracic wall. The thoracic wall cannot collapse. Can you collapse your thoracic wall somehow? Unless you have an accident or something, but this is bone. Cannot be collapsed, right? So here is a bone, the thoracic wall in general, adherent to the parietal, negative pressure with the visceral, and the vessel itself is attached to the lung. And this is what's keeping our lung inflated all the time. Just try and put some air in here, introduce some air, this area will collapse. Does it make sense? Once you eliminate the negative pressure somehow, the lung will collapse. The lung tend to collapse. This is normal. The lung tend to recoil. It's like a rubber band. If you leave it alone, it will become like this. The lung that you see, like this in the X-ray, just let it go. It will go like this. It will collapse. This is normal. But we have to keep it like this by the negative pressure that I was talking about. So why do we have the negative pressure again? One of the reasons is to keep the two layers together. The other reason is, does it ever become positive under normal circumstances, the interpleural pressure? Can it become positive? No, it cannot become positive at any time. So it's always negative. Negative what? That's change. Are you exhaling or inhaling? It can be -2, -3, -4, -5, -6. It's minus anyway, negative, right? So because you're having always a negative interpleural pressure, that's going to make the lung always negative if not the lung, the thoracic cavity is always negative if compared to anything else. And this is what's pulling the blood up. If you're asking why the blood which is in the venous system, in our legs for example, in our foot, the pressure is too low, right? Do you remember how the pressure changed as you go with the blood vessels? The highest being at the first part of the aorta, and it goes down, 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 down until you go to the veins, very low, and the lowest is inferior vena cava, right? So obviously it's under very low pressure. What makes the blood goes up against gravity? Let's say in the foot. What does it make it go up? We mentioned that in the circulatory system, and we said the muscles act as a pumping machine. We push it up. The valves will prevent it from going down if the valves are intact. Plus this, we have a negative pressure that keep on sucking the blood up. Okay, these are all the factors that help returning the blood back to the heart. Now, tidal volume. Tidal volume is the amount of air that moves in and out in a single respiratory cycle, which is this. How much air did I get? Half liter in average. Okay, you're sitting down right now, you get half in, half out, half in, half out. This is happening all the time. Is that the only thing that you can do? No, it depends on your activity. You can do half in, half out, tidal volume. Why did you call it tidal volume? Because it looks like tides, like the sea. It goes like this, up, down, right? The tide goes up and down, up and down. So you take half liter in, half liter out, half liter in, half liter out. This is under normal circumstances. Can you make it 1 liter in, 1 liter out? Yes. Instead of doing, you can do like, and you can make it 4 liters, right? You can make it more. But the tidal volume is the amount of the lung in single respiratory cycle under rest, under resting condition. This is called the tidal volume. Okay, so now, again, what kind of pressure is between those two layers? Negative or positive? Negative. What if you have an accident and you open this? The air will move in or out? In, of course, it's negative, right? So it will move in, accumulate in this area, will be sucked in because it's negative, and this will allow this piece of the lung to collapse, right? The introduction of air in here by itself is called pneumothorax. Pneumo means air. Thorax, pleural cavity, or the pleural space. So what's pneumothorax? Air in the pleural space. Are we supposed to have air in between the two pleural cavities, pleural membranes? We're not supposed to have any. It's one layer, fluid, one layer. No air. If you introduce air, pneumothorax. Atelectasis is this. Collapse of the lung. So the atelectasis usually depend on the pneumothorax. What's hydrothorax? It's not here, but what do you think? Water in the not in the lung. Which? The what? Plural, in the plural space. What was the pneumothorax? Air in the plural space or plural cavity. How about water? Hydrothorax. You see something like this? Hydrothorax. How about this? Just guess. Hemothorax. Blood in the thorax cavity, right? Okay. These are the muscles. I think we're familiar with these muscles. External intercostal, internal intercostal, and the diaphragm. We have also the innermost inside. These are all the regular muscles. We have some extra muscles that if you're doing strenuous exercise or if you wanted to move the chest wall a little bit more, you can use the extra muscles. And these are the extra muscles, the respiratory muscles, sternocleidomastoid, the scalene muscles, and the pectoralis muscle. So under normal circumstances, look at yourself right now. Are you using your sternocleidomastoid, for example? You're breathing lightly now. Are you using this muscle? No. Is it contracting? No. So you use these muscles only if you're doing forced respiration, active respiration, not under the resting conditions. Okay? So we have the diaphragm, we have the external intercostal muscles. These are the main muscles. And you have the accessory muscles. The accessory muscles is what I was just talking about. You only use it if needed, if you wanted to do active breathing. So inhalation is always active. Exhalation is usually, not always, usually passive, right? Inhale, try it, inhale. You're doing some effort, right? Let it go. This is passive. How about this? Inhalation, active. Exhalation, passive. Now I'm using my muscles, right? So it can be passive, which is normal, but sometimes it can be active if needed, okay? So inhalation is always active. Exhalation can be active or passive. Most of the time under resting conditions, it is passive. The diaphragm is using the main work, 75% of the work, and the external intercostal is doing the 25%. Anything else, only if needed. Sternocleidomastoid, serratus muscle, anterior pectoralis, scalene muscles. These are called the accessory respiratory muscles, meaning you don't use it under resting condition. You use it only in active respiration, only if you have to. Internal intercostal and transverse thoracic, which is the inside of the thoracic wall. This can depress the rest, so it can help you in exhaling. And the abdominal muscles, sometimes you use it for the same thing. You push, the abdominal muscles contract, pushing the abdominal viscera, and the abdominal viscera, like the liver, will push up the diaphragm. So only if you have to do forced exhalation. Are we following? The other accessory muscles like sternocleidomastoid, scalene, and anterior scalene, and these muscles are accessory muscles. During what? During active exhalation. These muscles are used as accessory muscles in active exhalation. So active inhalation, sternocleidomastoid, serratus, pectoralis minor. Okay? Well, how about exhalation? Active, these three muscles. Quiet breathing is what you're doing now. Quiet breathing. We're all quiet breathing. Maybe I'm not. Maybe I'm doing the forced breathing a little bit. But quiet breathing is breathing under resting condition. Like you're sitting down. This is quiet breathing. Forced breathing, if you're doing something active breathing. So the normal breathing is called eupnea. When you see EU at the beginning of any word, it means normal. Okay? EU is a prefix that means normal. Pnea, when you see it at the end of any word, it means air or breathing at this time. So quiet breathing, what's the quiet breathing? What you're doing right now. Active inhalation and passive exhalation, right? So this is dominated by the diaphragm. This is deep breathing, is diaphragmatic. Coastal breathing is shallow breathing. Elastic rebound is what I was just talking about, which is the lung is elastic, meaning it's like a rubber band. If you just let it go, it will exhale because of the elastic rebound. Forced breathing is called hyperapnea. And again, just use this word, this part, the suffix, P-N-E-A, means breathing. Okay? Eupnea, normal breathing. Hyperpnea, extra breathing or forced breathing. Hypopnea means low. So you can put three prefixes before this. Okay? Hyper, hypo, and you get it. It's talking about the breathing. Are you doing the quiet breathing, normal breathing, active or forced breathing, or less breathing? We will talk about this. So if you're doing hyperapnea, both inhalation and exhalation will be active. How about the quiet breathing? What was active and what's passive? What you're doing right now? Inhalation is active. Exhalation is passive. This is in quiet breathing. Hyperapnea or the forced breathing, both of them are active. So what's the respiratory rate? How many times do you breathe per minute? How many times do you think? Yeah, very close. Yeah, it's an average, and they have differences in this, but you can say it is somewhere, depending on the age, from 14 to 18. Anything in between would be fine. 16 is fine, 15 is fine, 17 is fine, somewhere in between. Respiratory minute volume. What's the respiratory minute volume? Do you remember the cardiac output? Do you remember that still? What was the cardiac output? Heart rate multiplied by stroke volume. This is the same thing. Respiratory rate multiplied by tidal volume. Tidal volume in the lung is the same as stroke volume in the heart. Respiratory rate in respiration is the same as heart rate. So multiply those two, and this will be called the respiratory minute volume. So if I say your respiratory rate is 20, okay, 20, and the tidal volume is half liter, what is your respiratory minute volume? Huh? 10? Yes. Okay, what's an atomic dead space? The dead space is the part that's not participating in respiration, the conducting system, the remaining conducting passageway. Do you do breathing or exchange of oxygen, carbon dioxide through your trachea, for example? Do you do exchange through the trachea? Like the oxygen cross the trachea and carbon dioxide? No. Bronchi, bronchioles. What's the only part that we do the actual exchange of oxygen, carbon dioxide? Alveoli and a little bit of? Which one? The respiratory bronchioles. Okay? The respiratory bronchioles. A little bit. Mainly it's the alveoli, plus some respiratory bronchioles, and the rest is all anatomic dead space. It's a dead space. What do you mean dead? I mean there is no exchange of oxygen and carbon dioxide. Why do you have it then? Just to conduct. So the conducting system is the anatomical dead space. Okay? So what's the actual ventilation? If I say you have 2 liters right now inside your respiratory system, are you benefiting from all the 2 liters? No. Not the whole 2 liters are reaching your lung. You don't exchange with the 2 liters. Part of it is the anatomic dead space, which does not undergo any crossing or any exchange. So the tidal volume, let's say it's half, minus the anatomic dead space, let's say it's 0.2. So the difference is the actual ventilation, which is the alveolar ventilation. I think that makes sense. Do you have more oxygen in the atmospheric air or inside your lung? What do you think? In the air is more. That's why it moves in and cross the alveolar wall, go to your blood. Do you have carbon dioxide more in or out? In, and that's why it moves out to the atmosphere. Okay? Okay, so the 2 factors that affect the alveolar ventilation rate are respiratory rate and tidal volume. Now look at this picture here. This is summarizing all what you can do. Look at the people. You know yourself. Okay, so what is this? Half in, half out. Half in, half out. What is this? What do you call it? Huh? Yeah, which volume? Tidal volume. So this is tidal volume. Okay. So in, out, in, out. This is what you're doing right now. Okay? How about this? Half in, half out. Half in, half out. And instead of half out, I'm forcing it more to the maximum. What is this part? This is an extra part that's called the expiratory reserve volume. This is the volume that's reserved for expiration, for active or forced expiration. So you can go half in, half out. Half in, half out. Can I go half in and then 2 out? This extra part, not talking about this half, the extra part is reserved for active exhalation. How about this? Half in, half out. What do you want to call this? Inspiratory reserve volume. It's the volume that's reserved for maximum inhalation or maximum inspiration. Okay? When you add the maximum inhalation and the maximum exhalation, this is called the vital capacity, which is this. Half in, half out. Half in, half out. How about this? The whole thing. This is the vital capacity. This is the whole capacity that you can do. Okay? With your maximum inhalation, maximum exhalation. Okay? So if you added tidal volume plus, what was this? Inspiratory reserve. Does the inspiratory reserve include the tidal volume?
Yes.
No. You go like this. Half in, half out. Half in. The inspiratory reserve is above the tidal volume. The expiratory reserve is under the tidal volume. So the tidal volume doesn't count. Okay? If you want to count it, that will give you this whole thing, which is the inspiratory capacity. This is your whole capacity. Okay? Did we get this? How about the expiratory reserve rate is under the half in and half out. Total lung capacity, the only part that's remaining, what's under this? Like this, look at this. Is there still a space in there, or is this over? The space is gone. You still have some space. You're not going to use it. It's not part of the vital capacity. You can't use it. Go to the maximum expiration, maximum exhalation. You can't use it. Okay? And this would be called the residual volume. The residual volume is the volume that's going to stay there to keep your lung inflated. Otherwise, you're going to collapse the lung. Okay? So after the maximum exhalation, the remaining part is the residual volume. And if you add the residual volume to the viral capacity, that's called the total lung capacity. Is that clear? Okay. And these volumes, this is what the pulmonologist or the pulmonary doctors, if you have a problem with the respiration or something, they use a machine that gives you something exactly like this. Okay? And it gives a report. This is his tidal volume. This is his maximum. And they will ask you to do what I just did. Okay? So this is the measurements of all capacities and volume, and this can give a good idea about what's happening in your body. I'm having a problem. What kind of a problem? I'm not sure. I'm having a hard time breathing. Let's do this. Tidal volume, just breathe normal, and then take the maximum inspiration, exhale, go back to normal. Take the maximum exhalation, go back to normal. And we measure those, so if you cannot get the whole air out, it means you're having a bronchial constriction, for example. Just giving you some examples. Okay, or if the half liter is becoming 0.3, so you're not respirating well. Like older people, for example, they cannot exhale and inhale to the full capacity, just like younger people. So this can be a helpful diagnostic tools. So we went through this in the picture. Vital capacity until you get to the total lung capacity. So this is basically the pulmonary function test. So you go to the doctor, I'm having a problem with my lung, any problem, they say do PFT. You go to the PFT, they give you this machine, breathe in this, give you a tube, breathe in this, and they will ask you what to do. The graph will come just like this, and it will give the report, PFTs. Now, the movement itself of carbon dioxide and oxygen across the membrane. This will depend on the partial pressure of these gases. What's the partial pressure? The partial pressure is the pressure of a certain gas within the rest of the gases. Like the gases here are oxygen, carbon dioxide, hydrogen, nitrogen, anything. Okay, we have a lot of gases. How about the oxygen only? If you measure the oxygen pressure only within all this air, this is called the partial pressure. So the partial pressure is the pressure of one of the gases, specific pressure for one of the gases. And the movement will depend on the concentration gradient. And this is what we were just talking about. Now let me ask you this. This is the alveolus. Okay, here is the air coming to the lung and going all the way until you reach the alveoli. Let's say this is one of the alveoli. Okay? And this is a blood vessel. Oxygen, oxygen, carbon dioxide, carbon dioxide. Do we have more oxygen in the alveoli or in the blood vessels? Alveoli, so travels in via what? What's helping it to go through? Concentration gradient. How about carbon dioxide? Is it more in the blood vessels or in the alveoli? Blood vessels, so it moves out from the blood vessels to the alveoli via concentration gradient. So the concentration gradient of the oxygen move it in, and the concentration gradient of the carbon dioxide move it out, meaning you have more carbon dioxide in the blood vessels than the alveoli, and the oxygen is the opposite. We have nitrogen, we have oxygen, we have water vapor, we have carbon dioxide. The oxygen is what you have to know, 20%. Okay? The vast majority is nitrogen. So if you analyze the air, you will see all of this. But the vast majority is nitrogen. You have some oxygen, about 20%, and the rest is vapor and carbon dioxide. Okay, we talked about the atmospheric pressure, which is 1 atom or 1 atmospheric, 760. This is the normal at the sea level. And here is Dalton law. The Dalton law say that the gas pressure contributes to the total pressure in proportion to the number of the molecules. You have more molecules, you have more contribution. Less molecules, less contribution. And Dalton law, again, let me say that again, any law or principle is important. Okay? I think I summarized all of this at the last slide, maybe a slide or two, I don't remember. And I'm not expecting to see mistakes, but I know that I will. For some reason, I don't know why. Okay? Please don't create mistakes in this. Okay? You have 2 slides, and you know that I'm going to use it for the matching, right? 2 slides. So don't do mistakes in this. So the partial pressure is the pressure contributed by each gas. Okay. Henry's law, simply, Henry's law is the law that the beverage companies used to make the soda. You know what's the soda? Or Pepsi, whatever, anything, any carbonated beverages, what is it? It's a carbon dioxide. Compressed, they put the carbon dioxide under pressure. Did you see these machines when you put the cup and get some Pepsi or anything else? You know what are these tubes? It's carbon dioxide. The tube that you see behind the machine, this is carbon dioxide, but it's under pressure. There is a machine that forces it in under pressure, and from the other side there is another tube that's bringing this colored water that have some whatever Coke or Mountain Dew, whatever the flavor is. It's water and this flavor, and the carbon dioxide come from another side under pressure, and it will be forced to interact and dissolve partially with the water, and this is Henry's law. So Henry's law is gas under pressure coming in contact with the liquid will dissolve. Okay? And this is obviously, of course, if you drink soda, you will easily know that this is a temporary dissolving. The gas is temporarily dissolved. Just shake it a little bit and see what happens, right? The gas will leave, and you can't even drink it. Leave it for some time. Can you drink it like 3-4 hours later? Most likely not. It doesn't taste like soda anymore. Yeah, right? So that's because this mixing or the gas dissolved temporarily. It's very easy to leave or dissociate. So Henry's law is about gas under pressure in contact with liquid will dissolve. The oxygen is very soluble. So once the oxygen moves to the blood, move from the alveoli to the blood, it's going to dissolve really fast. It's very soluble, okay? I mean carbon dioxide. Oxygen is less soluble. Nitrogen is very low solubility. So nitrogen, if it goes in, it's very hard to mix or become soluble. Carbon dioxide is very soluble. When the carbon dioxide moves in and it's going to dissolve in the water medium, what do you get? What do you get? When carbon dioxide dissolve in the water, what do you get? What's that taste of the soda coming from? It's an acid. Carbonic acid. Yes. So you mix carbon dioxide with water, you get carbonic acid. CO2 plus H2O, H2CO3. Okay? Carbon dioxide plus water, carbonic acid. So that's easy. Oxygen can dissolve in water or the watery medium a little bit. Nitrogen, too hard. Those two numbers are important. 40 versus 100. This is in pulmonary veins. So it's 40 for carbon dioxide, it's 100 for the oxygen. That's in the pulmonary vein. Does that mean it's oxygenated already or deoxygenated? Yes. What do you think? Pulmonary vein. You just had your lab practical, or you will have lab practical on Thursday. You can't forget. And this was in the lab practical. Pulmonary vein. Oxygenated. Yes. This is after being full of oxygen. 100. This is the best. 100. This is what we need. Okay? And 40 is after we lose the carbon dioxide, it will become 40. So this is the pulmonary veins. Okay, so again, we are counting on carbon dioxide and oxygen cross the membranes depending on the concentration gradient, right? We mentioned that. Plus, they are lipid soluble. So it's easy for them to cross the membranes of the cell. Do you remember what was the membrane? What's the main constituent of any cell membrane? A double layer of? What is it? Lipid. With what type of lipid? Phospholipid. Do you remember this? So oxygen can easily cross the membrane, carbon dioxide can easily cross. Okay, so this is even make it easier. So you have two factors now. You have the concentration gradient and you have the lipid solubility of those two gases. On the other hand, in the interstitial fluid, the oxygen is 40 and the carbon dioxide is 45. What was the other numbers? 40 and 100. Okay, so this is first of all, what was the pressure in the pulmonary veins? 140, right? How about inside the heart? 140. How about in the aorta? 140. Did it change? Did you do any exchange yet? Or these are just conducting vessels? Nothing have changed, right? So it's the same thing. It goes to the arteries all the way until you get to the capillaries. So now at the level of the capillaries, and this is the cell. So the pressure here is 40 and 100. What's the 100? Oxygen. And what's the 40? CO2. How about the interstitial fluid, which is this fluid in between the cells? What's the pressure? Oxygen? 40. And what's the carbon dioxide? These are the numbers that you need to know. So oxygen in the blood vessels or in the capillaries is 100, and the interstitial fluid is 40, so it will move in or out. From what to what? From the vessel to the interstitial, from the interstitial to the capillaries. Oxygen. Capillaries to the cells? Are we all following? How about the carbon dioxide? From 45 to 40. Concentration gradient. More concentration to less concentration. So carbon dioxide move from the interstitial fluid to the capillaries or to the blood, and oxygen on the other hand move from the capillaries to the cells. Okay? So 40, 100, 45, 40. Okay? So if you can draw this or write down this or something, that would be good. Okay, so now as the carbon dioxide and oxygen moving in the blood, they will not only be dissolved in the plasma. What's the plasma? The fluid part of the blood, right? And the other part is the cellular component, cells, white blood cells, red blood cells, platelets, right? So it will be attached to the part of it will be dissolved in the plasma, small part, and another part will be carried or transported by red blood cells, hemoglobin. Each molecule, of course we know RBCs contain, what are the contents of the RBCs? What's inside the RBCs? Hemoglobin? Hemoglobin, is that true? What's the hemoglobin? Hemoglobin. Globin is a protein, amino acid. Heme is iron plus other things. Each one iron can attach, or each molecule can attach to 4 oxygen at a time. Okay? And when the oxygen attached to hemoglobin, what do you want to call it? Oxyhemoglobin? Yes, oxyhemoglobin. Oxygen in the hemoglobin. What do you call it if it is carbon dioxide attached to the hemoglobin? Does anybody remember the term? Carbamino. Carbamino hemoglobin, which means carbon dioxide attached to hemoglobin. So oxygen will attach to the hemoglobin. You have more oxygen, more hemoglobin, more attachment to the hemoglobin, until a certain level that the hemoglobin will be saturated. Okay, this is called hemoglobin saturation, when the hemoglobin gets saturated with oxygen. Okay, what affects the capacity or the ability of the hemoglobin to carry oxygen? The pressure of oxygen is one thing. The pressure of oxygen. You have more oxygen, more pressure of oxygen, more attachment to the hemoglobin. So this is the first factor. Number 2, the pH. Is the pH normal, 7.35, 7.45, or is it moving toward acidity or alkalinity? That's going to change how the hemoglobin carry oxygen. How about the temperature? It's going to increase. Metabolic activity in the RBCs itself. These are the factors that affect how hemoglobin attached to oxygen. And this will get us to the oxyhemoglobin saturation curve. There is a curve, you increase, this is the curve. You have more oxygen, more hemoglobin carrying oxygen. So you increase the oxygen pressure, the hemoglobin will carry more. Increase more, until you get to a certain limit, which is this, hemoglobin cannot carry anymore. Okay? So just to make it easier, let's say I'm asking you to help me. Okay? Can you carry one of these chairs and put it out of the classroom? Yeah, that's fine. Can you take 2? Okay. Can you take 3? That's hard. Can you take 4? That's the maximum. Can you take 5? No, I can't. Okay? So the more chairs I give you, the more you carry until a certain limit. So the more pressure of oxygen, the more hemoglobin carrying oxygen. Until it goes to the maximum saturation, the hemoglobin is full, I carried as much as I can, nothing else can be done, and this will give us to the plateau, which is this surface here. What affects the hemoglobin carrying? Why would the hemoglobin carry more oxygen when the pressure increase or not? So you increase the, like what force you, if I ask you, carry 2 chairs, why would you say yes? What make you say yes? Why don't you just say no? I can't, right? You can, but can you refuse? Maybe. What affects the ability of hemoglobin to carry oxygen? What we just talked about, the temperature, the pH, the metabolic activities of the RBCs. More PO2, greater saturation. And the greater saturation is shifting to the right versus shifting to the left. So this curve can move right or can move left, make it easier to release carry and release oxygen right or left. So if you have more oxygen, the hemoglobin will be saturated more. Now carbon monoxide. Carbon monoxide, we didn't talk about this before. We always talk about oxygen and carbon dioxide. Carbon monoxide is more poisonous than carbon dioxide because it's very strong, have very strong attachment and affinity to hemoglobin. Meaning, if this is the hemoglobin and there is oxygen, carbon dioxide, carbon monoxide will push the oxygen, carbon dioxide away and attach to the hemoglobin. So the affinity or the attachability is a lot higher, stronger binding, and it can actually take the place of oxygen. You have hemoglobin here, get oxygen, carbon dioxide, and carbon monoxide. Carbon monoxide will occupy the vast majority of the hemoglobin. It will fight with the carbon dioxide and oxygen and take the place. Okay, and this explains why it's so poisonous. It's worse than the carbon dioxide because it's stronger to attach. It can actually displace oxygen away. Okay, and this is the carbon monoxide poisoning, and this is usually what comes from the fuel burning, like the exhaust system of the car. And I don't know if you heard about this or not. There was one time in the news that somebody puts another person in the garage, and he connected the exhaust system to the inside the garage. A few minutes, he died because of the carbon monoxide. It's full of carbon monoxide. Is it only carbon monoxide? No, there is a lot of things in the exhaust system of the car, but the most poisonous is carbon monoxide. It just takes a couple of minutes, and he's dead. So hemoglobin saturation is affected by pH, temperature, and metabolism. So what happens if the pH drops? This is the oxygen saturation curve, like this, right? Approximately. Can it be like this or like this? Yes. This is called shift to right, and this is called shift to left. I'm not going to go through the mathematics or statistics or anything else. Just understand just the concept as a general idea. It can move to the right, it can move to the left. Okay? When the pH drops or the temperature rises, hemoglobin release oxygen, which is called shift to the right. That's all what we need to know. Okay? So shift to the right, pH drops or temperature increase, that will shift to the right. What do you mean shift to the right? Easier release of oxygen. That's it. That's all what we need to know here. Okay? If the pH increase or the temperature drop, less oxygen will be released, and this is called shift to the left. Did you get this? That's all what we need to understand here. The oxygen saturation curve. If it moves to the right, release more oxygen. If it moves to the left, release less oxygen. What move it to the right? What move it to the left? What move it to the right is pH drops or heat. Temperature increase. What shift it to the left and make the oxygen, the hemoglobin attach to the oxygen, don't want to release it, pH goes up or temperature goes down. It's the other way around. Did you get this? Shift to the right, shift to the left. This effect is called the Bohr effect. This effect, which specifically the pH part, not talking about the temperature part, the pH part of the shifting right and left, that's called the Bohr effect, which is basically what changed the pH. What pH drop means, or the pH goes down. What does it mean? Acidity or alkalinity? More acidity. What makes it more acidic? Carbon dioxide. Carbon dioxide, if you have more carbon dioxide in the blood, carbon dioxide will react with water, making what? Carbonic acid. So it's carbonic acid, acid, isn't it acid? Acidity, what happened to the pH?
Down.
Goes down. What happened to the oxygen saturation curve? Move to the right or left? Right, releasing more oxygen. This is the Bohr effect. Okay? The BPG, or the lactic acid, this is a product of glycolysis, and if it increases, it will shift to the right too. That's all what we need to know here. What's the difference between the fetal hemoglobin and the adult hemoglobin? The fetal hemoglobin is a big thief. Okay? He tried to steal the oxygen from the mom all the time. So the fetal hemoglobin has more affinity or attract more oxygen, attach more to the oxygen. Otherwise, does the fetus breathe? No, the lungs are not even working yet. He get all the oxygen from the mom, so the fetal hemoglobin has to be different. It has to be having more binding ability to the oxygen to be able to take the oxygen from the mom. This is the difference in the hemoglobin. Where do we produce the carbon dioxide? If you look at this. We said we have carbon dioxide 45 in the interstitial fluid, and we have 40 in the blood, right? What make it 45? Where is it produced from? From the metabolic processes. You get the glucose, enter the cell, break it down, burn it, get pyruvic acid, enter it to the mitochondria, break it down more, and you end up having carbon dioxide and water. Do you remember this? Or? Serial respiration, right? Where is the carbon dioxide coming from? It's 45. Why? Why it's 45? Because this is the end product of breaking down the glucose. Do you still remember this or not? This is your cell. It needs glucose all the time. Glucose enters the cell. You break it down into 2 pyruvic acid. Then if you have oxygen, it goes to the mitochondria, and you break it down further. To what? To carbon dioxide and water. Do you still remember this? This is where the carbon dioxide came from. The vast majority of carbon dioxide will be in the form of carbonic acid, which is the carbon dioxide dissolved in water, 70%, and the rest will be attached to the amino group of the hemoglobin, and just a little 7% is in the plasma. What's the importance of the bicarb? Is a bicarb, if I add bicarb to a solution, does it make it alkaline or acidic? How about if you add hydrogen? Both of them acidic? So when you add hydrogen to a solution, you make it acidic. When you add bicarb, alkaline. Okay? So bicarb is, if it's added to a solution, it will make it alkaline, versus hydrogen will be the opposite, and this is why we have to generate the bicarb all the time to take care of this process. Do you remember the buffer system? I talked about this in a video for preparation of the lab practical, and the bicarb is released from the pancreatic secretion and from in the bile. Did you see this? So this is the function of the bicarb, and there's a mechanism that's called the chloride shift. We don't have to know the details, but this is how we make the bicarb available for the buffer. Control of respiration. How do we control our respiration? What is controlled in the respiration in the first place? What is the control? What can you control? Can you control the respiratory rate? Can you breathe faster or slower? Can you control the depth? Right? Exactly like the heart. You can increase the heart rate or decrease it. You can increase the force of contraction, you can decrease it. Same thing here. So you can breathe faster or slower. This is one. You can breathe shallow or deep. Right? So there are different ways to control the regulation, to regulate the respiration. And basically, the first one is local, and it depends on the carbon dioxide level. If this cell is producing a lot of carbon dioxide will go to the blood, asking for more blood to come. This is called the local regulation. Carbon dioxide produced from the cells, it will go and dilate the vessels so that more blood come to take the carbon dioxide away, right? The second thing that's local is the lung perfusion. And think about this. If this is a lung, okay, and the blood vessels are coming to the lung, if this part of the lung is not working, dead, do you want to send more blood to this area or less blood? Less. You want it actually to stop the blood going to this area. It's dead. Why would you waste your blood sending it to an area that's dead, that's not going to do any exchange, right? So if the area is dead, that was going to constrict the blood vessels going to that area, and this is one of the local mechanisms. Respiratory centers. The respiratory centers that regulate the respiratory rate and the respiratory muscles. You have respiratory centers in the pons and the medulla, and these are going to change the rates, the respiratory rate, and the depth of the breathing. So where is the location? Pons and the medulla. Is it the same? No. Which one is above and which one is under of those? The medulla is above the pons? Is that true? How does it go from above down? Midbrain, followed by pons, followed by what's under the medulla? You guys forgot already? Seriously? What is this, and this, and this? What is this? What is this? What is this? What is this? This. Spinal cord, and what's this? Midbrain, what do you call this? Brainstem. So the pons is above the medulla, right? So the medulla is setting the basic rhythm for respiration. So the medulla will do the basics. Will tell you breathe 18 times per minute. That's it. If you wanted to change that, the pons will have an upper hand. So it's not the same. It's not, both of them are controlling, yes. But what's the exact function or difference? The medulla set the basic rhythm, while the pons can modify that. Okay, so it has some sort of upper hand. Quiet breathing versus forced breathing. We talked about this already. So you have the respiratory centers in both the medulla and the pons. The ones in the medulla set the basic rhythm. The ones in the pons are called apneustic and pneumotaxic centers in the pons. Okay? The apneustic center versus the apneustic center will stimulate. The pneumotaxic center will inhibit. And this is how you modify the respiratory rate. Okay? SIDS, sudden infant death syndrome. This is a disruption of the normal reflex in infants. Okay? And this is basically a problem with the connection between the pacemaker and the respiratory centers. There is something in the brain that disrupts this connection and can cause sudden death of the infants, and it is due to disruption of the respiratory reflex. What's the respiratory reflex? This is the reflex that controls the pattern. Should you breathe quietly or forced, fast or slow? So the breathing pattern will change with the respiratory reflexes. Now the respiratory centers itself. What make the respiratory centers send the signal to the respiration and increase it or decrease it? Why would you breathe more or less? What are the factors affecting that? It is the level of P means pressure. Okay? So the pressure of carbon dioxide, the partial pressure of carbon dioxide, the partial pressure of oxygen, or the pH. These are the three factors that work on the chemoreceptors to modify the activity of the respiratory centers. Are we following? The baroreceptors, on the other hand, baro means pressure. Chemoreceptors, chemo means chemistry, which is oxygen, carbon dioxide, and pH. So the baroreceptors at the aortic arch and the carotid sinus, or aortic and carotid sinus, are going to be are sensitive to the change in the blood vessels, and it's going to modify the heart rates and the lung respiratory rates accordingly. Now the connection between the chemoreceptors and the respiratory centers. Where is the location of the chemoreceptors? In the aorta and the carotid artery. Do you remember those two? The aorta and the carotid coming out of it. So what will carry it is nerve number 9 and nerve number 10. 9 from the carotid and 10 from the aortic. Can you remember this? This is important. Okay? What take the signal from the chemoreceptors to the brain? What's the pathway? Which nerve? 9 and 10. 9 from carotid, 10 from aortic. And this will modulate or modify the depth and the rate, depending on these factors: oxygen, carbon dioxide, and pH. Hypercapnia. What's capnia means? Capnia. Capnia means carbon dioxide. Hypercapnia, increased carbon dioxide. Hypercapnia. Hypoventilation. When you ventilate less, breathing less, that can cause hypercapnia, right? If you breathe less, you don't get rid of carbon dioxide, so carbon dioxide accumulate, which is called the hypercapnia. Okay? Hyperventilation will cause hypercapnia or hypocapnia. What do you think? Hypocapnia. Why? You breathe more, you get rid of more carbon dioxide. Carbon dioxide inside goes down, right? Because you get rid of a lot of it. Baroreceptors, on the other hand, same spots approximately, carotid and aortic baroreceptors. They will affect both the blood pressure and the respiratory. When the blood pressure goes down, the respiration increase, and when the blood pressure goes up, the respiration decrease. Why? Why? Why when the blood pressure goes down, you have to respirate more? Can you tell me? Why? Blood pressure goes down. Why do you have to breathe more? Because when the pressure goes down, it means less blood going to the organs, less oxygen going to the organs. So you add more oxygen. So even though less blood is going, but it's carrying more oxygen, which is enough. Did you get this? Okay. So the baroreceptors, even though it monitors the blood pressure, but it affects the respiration as well. Hearing brewer reflex. This is an inflation reflex and deflation reflex, and this is what's preventing the over expansion. Protective reflexes, these are the reflexes that are protective, which is when you cough, for example. If there's toxic vapor chemicals or anything else, you're going to start sneezing, coughing, and you can get to the laryngeal spasm, which is bad actually, but it's kind of supposed to be a protective mechanism to close the larynx so that this does not enter. And what's the difference between sneezing and coughing? One is from the upper part, and the other one is from the lower part. Coughing is from the lung itself, from the alveoli, inside. Sneezing is from the upper part of the respiratory system. Apnea is when you stop breathing. Laryngeal spasm is the spasm temporary of the larynx, and this is protective to prevent things from coming in. There are other factors that affect the respiration, like strong emotion. If you feel emotional, or you feel like sad or happy or something, you know that this will affect the respiratory rate, stress, or if you're anticipating something like, did you post the grades? Did you post the grades, right? You'll be breathing more. Did you post the grades? Okay, or exercise. Even before you start the exercise, you will start to breathe more. Before birth, there's no respiration. During delivery is the first breath, and then the breathing continue. Aging, everything deteriorates. Important concepts, I will do that next time. But here is one slide, and here's the other slide. I summarized everything that can be used for the matching. I'm not expecting any mistakes, please.